A 4-stroke engine can take in only so much air. The amount of fuel it needs for proper combustion depends on how much air it takes in. Engineers calculate engine airflow requirements using 3 factors: engine displacement, engine revolutions per minute, RPM, and volumetric efficiency. To increase engine effective power, we must increase displacement, rotational speed, or mean effective pressure. Increase displacement by enlarging the volume of each cylinder. Or increase displacement by increasing the number of cylinders. But this results in larger and heavier engines. The idea of rotational speed relates to the inertia of the rotating parts, which becomes more significant as the engine spins faster. However, increasing rotational speed is limited by mechanical stability constraints. The volumetric efficiency is defined as the ratio between the actual volume of intake air, VA, drawn into the cylinder and the theoretical maximum volume of the cylinder, VD, during the intake engine cycle. The actual intake air volume can be calculated as a function of air mass and air density. The more air and fuel that can be packed in a cylinder, the greater the density of the air-fuel charge. The principle of charging is simple. The engine needs oxygen for combustion, which it obtains in the intake itself. More air means more power, but the delivery rate is physically limited unless a turbocharger is used to blow more air into the cylinders. With the extra oxygen, more fuel can be injected, combustion pressure and torque rise. Charge density refers to the amount of air-fuel mixture introduced into the cylinders. A turbocharger, or turbo, is a centrifugal compressor powered by a turbine that is driven by an engine's exhaust gases. The exhaust gases drive the turbine wheel, which is connected to the compressor wheel through a shaft. The objective of a turbocharger is to improve an engine's volumetric efficiency by increasing the intake density. A turbocharger uses some of the heat energy that would normally be wasted. The turbine inlet receives the exhaust gases from the engine exhaust manifold, causing the turbine wheel to rotate. This rotation drives the compressor wheel, compressing ambient air and delivering it to the engine's air intake manifold at higher pressure, resulting in a greater amount of air and fuel entering the cylinder. The compressor is one of the 2 primary sections of a turbocharger, along with the turbine. Turbocharger compressors are generally centrifugal compressors. A turbocharger's compressor is the cold side of the turbocharger that draws in and compresses air to force more of it into the engine's combustion chambers. Driven by the turbine, the compressor increases air density, enabling the engine to burn more fuel and delivering a significant boost in power and torque. The turbocharger compressor consists of 3 essential components: the compressor wheel, the housing, and the diffuser. The compressor wheel's blades, nose, and hub draw in air and accelerate it to a high velocity. The compressor wheel is connected to the turbine by a forged steel shaft. As the compressor wheel spins, air is drawn in and is compressed as the blades spin at a high velocity. With the rotational speed of the compressor wheel, air is drawn in axially, accelerated, and then expelled in a radial direction. Compressor wheels are balanced on two planes, the nose and back wall. Many types of compressor wheel designs have been used over the years. Each one has its own advantage and type of use. The blades emanate in a straight line perpendicular to the axis of rotation. All blades are full length. Every other blade is shorter than the full blade next to it. The compressor housing, like the compressor wheel, is typically made from an aluminum alloy. The housing is the shell that encloses the compressor wheel. The spiral shape of the compressor housing gathers the high-velocity air and channels it toward the engine's intake. The compressor housing is designed to convert the high-velocity, low-pressure air stream into a high-pressure, low-velocity air stream through a process called diffusion. After the air exits the compressor wheel, it passes through the diffuser, which slows down fast-moving air from the compressor wheel, converts its kinetic energy into pressure energy, and directs it smoothly into the compressor housing. The function of the diffuser is to convert the rapidly compressed and high-speed air leaving the compressor wheel into static pressure as it fills the volute. Most diffusers used in automotive applications are vaneless. The vaneless diffuser is not an actual component, but rather the optimized path for the air as it leaves the compressor wheel on its way to the compressor housing volute. The vaneless diffuser is formed by the parallel walls between the compressor cover and the bearing housing face, or seal plate, depending on the turbo design. The vane-type diffusers are extremely efficient but have limited flow ranges and are therefore seldom used in automotive applications. It is mounted in the compressor side of the turbocharger, between the compressor wheel and compressor housing. The turbine provides the rotational force needed to compress ambient air to a positive pressure. The gas, restricted by the turbine's flow cross-sectional area, results in a pressure and temperature drop between the inlet and the outlet. This pressure drop is converted into kinetic energy to drive the turbine wheel. The turbine has two principal components, the turbine wheel and the turbine housing. The turbine wheel and shaft assembly is commonly called the turbine wheel. It is the most critical and costly of all turbocharger parts. The turbine wheel is turned by the expanding exhaust gases. The turbine wheel is connected to and rotates with the central rotating shaft. The central rotating shaft supports the two main parts of a turbocharger, the compressor wheel and the turbine wheel. The turbine shaft is typically induction hardened only in the bearing journal area. This is for wear purposes. In most turbine shafts, the threaded portion of the wheel features rolled threads rather than cut threads, which creates a stronger shaft once torqued with the compressor wheel in place. The exhaust gas is guided into the turbine wheel by the housing. The energy in the exhaust gas turns the turbine. Once the gas has passed through the blades of the wheel, it leaves the turbine housing through the exhaust outlet area. The volute progressively has a smaller and smaller cross-sectional area. As the exhaust begins to exit the housing, exhaust energy is lost. The tongue of the turbine housing forces the remaining exhaust gas energy in the volute to exit the housing. While there are many specialty turbine housing types, the two most common are open and divided housings. In single-scroll turbos, all exhaust gases are channeled into the turbine housing through a single entry, spinning the turbine wheel. Not as efficient at scavenging exhaust gases compared to twin-scroll turbos. A turbo exhaust manifold collects exhaust gases from an engine and funnels them into a single outlet to power the turbocharger turbine. The exhaust manifold separates exhaust gases from different cylinders, channeling them into two separate scrolls within the turbine housing. This allows for more efficient use of exhaust pulses. The divided housing utilizes a divider wall in the turbine volute to isolate the exhaust path from the exhaust port to the tip of the turbine wheel. The turbo center housing rotating assembly is the core component of a turbocharger, containing the shaft, bearings, and the attached turbine and compressor wheels. It is the central section located between the compressor and turbine housings. The turbo bearing system may appear simple in design, featuring one or two bronze bearings, and sometimes a separate thrust bearing, but it plays a crucial role, ensuring that the wheels keep spinning without any housing contact. The two main types of turbocharger bearings are Hydrodynamic Journal Bearings and ball bearings. The Hydrodynamic Journal Bearings are designed such that brass-free floating rotational bushings, rotating at about half shaft speed, are situated between the stationary center housing and the rotating shaft. This allows these high-speed bearings to be adapted, as there is no metal contact between the shaft and bearings at any operating point. Hydrodynamic journal bearings utilize a pressurized film of engine oil that flows through the bearing assembly to lubricate and support the shaft. Besides its lubricating function, the oil film in the bearing clearances also serves as a damping function, which contributes to the stability of the shaft and turbine wheel assembly. The oil also acts as a coolant, taking away heat generated by the turbine. There are two types of hydrodynamic journal bearings, fully floating and semi-floating. The fully floating journal bearings are two bearings that rotate freely between the shaft and the housing, at roughly half the speed of the shaft. The oil creates two films, one between the center housing and the bearing, and another between the bearing and the shaft. The fully floating bushing supports forces in the radial direction. As the gas forces acting on the compressor and turbine wheels in the axial direction are of differing strengths, the shaft and turbine wheel assembly is displaced in an axial direction. The axial bearing, a sliding surface bearing with tapered lands, absorbs these forces. Two small discs fixed to the shaft serve as contact surfaces. The axial bearing is fixed in the center housing. A semi-floating ring bearing system is a one-piece bearing used in many smaller turbos. It is a special form of a sleeve bearing system. The ring is fixed against rotation, and the outer oil film mainly acts as a squeeze film damper to control shaft vibrations, while the inner oil film provides lubrication. Ball bearings combine the functions of journal and thrust bearings into a single package. Ball bearing designs require less oil consumption than journal bearing designs. Ball bearings utilize a system of balls, often ceramic, and races to achieve lower friction, faster spool-up, and improved performance. Ball bearing turbos are often used in high-performance or racing purposes where quicker spool-up and better efficiency are critical. The design of ball bearing turbos involves more complexity, and is therefore harder and more expensive to rebuild. A wastegate is used on many turbocharged engines to limit and control boost pressures. A wastegate actuator is a control device in a turbocharged engine that regulates the maximum boost pressure by controlling the exhaust gas flow through the opening and closing of the wastegate valve. Wastegate actuators are generally associated with either internal or external wastegate setups, and their control can be pneumatic or electronic. Pneumatic actuators are the most common type of actuators in traditional systems, as they control air pressure and move the diaphragm to regulate the boost. Electronic actuators are found in more advanced turbo systems. They utilize the engine's electronic control unit, ECU, to operate an electronic servo motor for more precise and dynamic control over the wastegate. A wastegate actuator utilizes a diaphragm and a spring to open or close a wastegate valve in the turbine housing, directing exhaust gases away from the turbine wheel once a predetermined pressure is reached. The actuator diaphragm connects to a rod or linkage, and it is a flexible membrane that responds to pressure changes of a turbo without any contact with other components. The spring holds the actuator shut until the boost pressure reaches the designated level. The actuator's mechanism can be built into the turbocharger housing, internal, or be a separate unit mounted outside, external. External wastegates offer greater flexibility in sizing and routing options. The primary function of the wastegate actuator is to divert excess exhaust gases away from the turbocharger's turbine wheel, which prevents the turbo from overspeeding and causing engine damage. The wastegate valve controls the boost output of the system. In other words, it manages the turbine's speed to prevent it from overspinning and regulates the compressor's speed. The goal is to maintain the boost pressure within a safe range. At low boost pressure, the spring holds the wastegate valve shut, allowing all exhaust gases to flow through the turbine to help the turbo spool up and build boost pressure. When the boost pressure reaches a preset level that exceeds the spring tension, it pushes on the diaphragm and a connected rod, causing the wastegate valve to open. This open wastegate allows some exhaust gases to bypass the turbine, which limits the turbine's speed and consequently maintains the boost pressure at a safe and optimal level.